Recording.
All right, let's go ahead and finish up today. Oops, let me turn my screen on. Originally, I said we are going to try to get to chapter 7. Reviewing all the material in chapters, the rest of chapter 6 and all chapter 7, that would have been just too much for you, because that in itself would take up as much time as the first 5 chapters. So what I'm going to do is we're going to stop the grading at chapter 6. I'm still going to send you all the chapter 7 and 8 notes and everything, but you won't be responsible to do it as homework. But 7 and 8 are the meat of the subject, because it gets to the last part of chapter 6.4 we're going to talk about gets into hypothesis testing, which is the whole reason we're doing this stuff, is so that we can test how accurate our results are from our hypothesis and our studies. But so I'm going to take away that level of stress off you. So just worry about chapters 1 through 6, and 7 and 8. I'll send you all for your FYI, which I strongly suggest you look at that when you have time, but you won't be tested over. Because I'm looking over the grades. Some people haven't even gotten to chapter 3 yet. So yeah, you have to get to it. I'm giving you until Sunday at 10 o'clock or Sunday at 11. Say due date. Sunday, 11:59 p.m. Yeah, you're gonna hold that against me.
No, it's just around.
But don't wait until the last minute to do it, because I can't tell you the number of times at Sunday at 11:04 I said, well, the computer kicked me off. I was about to start my homework. I was on chapter 2. I could have done it all. You liar. Yeah, it happened. So yeah, it's that now. I mean, I've had even worse than that. When people haven't even started anything, said I was going to wait till the last day and do everything, but it finished one hour early because it was on Eastern time zone instead of Central. I would go back on the computer to look at it. Said they haven't even started any of their work, and they sent me the message within the hour it closed, and so. But that was my oversight. So don't wait, because I will not take any sympathy calls or text messages. If it does cut you out at 10:30 or 10 o'clock, so be it. You were supposed to have it done by this week in the first place. So every second after that is a gift. So do not complain about it shutting off early if it does. All right. The other day yesterday we talked about the first part of chapter 6. What do we talk about? What were the topics? Z-charts. What are the Z-charts? So the Z-score. What does the Z-score represent? When can you use Z-scores?
Or the chance of getting
Yeah, only used when your data is normally distributed. Again, mathematics is nothing but definitions. Once you know definitions, you keep on going. What does normally distributed mean? Well, that's increasing order. But normally distributed, the data has a bell-shaped curve. But yeah, you always want to have your data increasing order. Whenever you have any statistical analysis, put it in increasing order, so that way you can find out where the median is, or the mode, what all that stuff is. What does bell-shaped curve look like? You can, but that's later on in the book. right now, because everything, because remember, values in your G chart and your T chart are all where your population mean is equal to 0. And your standard deviations are 1. So your population is, the mean is 0, and the standard deviations are 1. Together, both of those things together will now make it easier for us to determine if our z value is negative 1.20. What does that tell us? What is that going to tell us when we look at the chart? We have to look at the negative chart. So let me get that up there. Yes, it's exactly. It means to the left of the mean. Since it is negative, let me see. So we go to which number? Yeah, on the left-hand side of the column, we look at these numbers. This number here is on the top. So we go to negative 1.2, and 0 is the first number. So we get negative 1.2. And on the top, it's 0.00. In this chart, it gives us 0.1151. So at negative 1.20, we get 0.1151. What does that number represent? Well, yeah, let's go percentage first, because this number here represents a percentage. The percentage of data that's to the left of that Z score. So it tells us that there's 0.1151, or 11.51% of the data that falls below that value. It's symmetrical. So if I had right here, if I had another line right here at Z equals positive 1.20, and I want to know this area, what would I do? Okay, let's look at the positive chart. So we have 1.20, 1.2, and there's 0. It's 0.8849. So this one, but remember, look at the picture. It represents everything to the left. So all of this stuff here is 0.8849. Right. So, or you can just use this number, because it's symmetric. So if you want to know what's on the right-hand side here, use what's on the left-hand side here, take away the negative. It's just because negative 1.20 and 1.20 is going to have the same value. Let's check it out. Since the whole area under the curve is 1, we have 1 minus 0.8849 gives us 0.1151, which is exactly what it was over here because of symmetry. So you have to be very careful about what number you use for what and what picture. Now, are all charts this way? No, some charts have it designated different ways. So they take the number and find it to the right. So you have to be very careful. Look, that's why they always come with pictures that tells you what the Z values represent. Okay, what if I had a Z value of negative 0.91 and a Z value of 2.22? I want to know the area between there. How would you find that? No, you can't answer. Remember, what part of the graph does the chart give you? To the left. So first off, let's look at this one. This Z value was negative 0.91. So we have to go to the negative chart. Point negative 9, 1 is the second. This is 0, 0. This is 0, 1. So it's 1814. So this area here is 1814 in our chart. And the positive side, the 2.22, 2.2012 is 0.9868. This is 0.202, 9868. So all this area here is 0.9868. I only want the area between here. How do I find that? Anybody? The 2.22 is all the area from this line all the way to the end. 0.91, negative 0.1, is only from this line on out. I want what's between there. So how do I find it? Go ahead. How do I find it?
It's a 9, 6, 8 minus the 1. Then you should get 0.805.
So that is the area. That's the difference of the two. Very good. That's this area. You take away the bigger one minus the smaller one from the bigger one, and whatever's left is between there. All right. What if so what's the formula for the Z-score? No. Well, Z equals, yes, X minus with the mean, the sample, its mean, then the standard deviation, right? And for populations, And remember, all of these have multiple formulas depending on what kind of data set you have, whether you have a simple random sample, whether you have an interview type data set, if you have binomial, if it's either yes or no, on, off, good, bad. What is the z-score of an or with an area? Oop, let me do this again. Zero point zero zero 0.0017. So is this z-score going to be positive or negative? There's a separation of these two. If you have a z-score that's negative, you're going to have a small value. If it's positive, it's going to be larger than 5. Why is that? Can you tell me using a picture? Exactly. It has to do with a bell curve. Remember, in the middle, it's 0. To the left, it's negative. To the right, it's positive. The whole area of the bell curve is what? The whole area of the bell curve is 1.000. So that means right in the middle, that's 50% or 0.5000. So 5% is 50000, which means anything over here, here's 0%, and here's 100%. In decimal, should be 49.99. But so you see, everything over here goes from 0 to 50%, or actually from 0 to 49%. 49%, 49.99. And everything over here starts at 50.001, goes on to 1. That's placed in the wrong place. So just by looking at the z-score, you can tell me where it's located. So in our value, 0.0017, we know it's going to be in which chart, positive or negative? It'll be the negative chart. So we work backwards now. I gave you the area. The numbers here are the areas. The z-score is on the outside. So we have to find 0.0017. Unfortunately for us, it's increasing in values. So 0.0017 is right there. 0.0017. So that is 2.93. So the z-score is negative 2.93. Has the area 0.0017. So far, so good. The mean is 28. 28 even, 0.00. And the standard deviation is 5.00. If the area is 0.0017, what X value corresponds to that area? So how would you go about solving this? Do we know any formula there? Yeah, since we're dealing with area under a curve, what area are we talking about? The z-scores. What's the formula for z-score? Right, x minus x bar. So the first thing we have to do, find the area. What z-score corresponds to that? We just worked that out. Negative 2.93. So we know z is negative 2.93. What else do we know? We know S, that's the standard deviation. That's 5. 28. Yeah, and we don't know what X is. So we have to solve for X. How do we do that? Right, multiply by 5. Both sides.
Then you like to get a calculator back there. For you.
So we multiply both sides.
I already did it, that's fine.
So now we multiply 5 times negative 2.93. That's negative 14.65. Now we add 28 to both sides. So the 28's cancel there. So X is equal to 28.00 minus 14.65. 5331. So the X value we're looking at is that. So we have to be able to go both directions. If I give you the X value, you tell me what the Z-score is, and then from there you tell me the area. If I give you the area and everything else, you can tell me what the Z-score is. If I give you both the area and the Z-score and all that sort of stuff, you can tell me what the X is. So far, so good. I know it's simple when I do it, but the second you walk out that door, it all gets erased. It's a de-res door. Now, here's the stuff that I want to cover for today. In our section, we also talk something about critical values, because we're going to need critical values when we start doing hypothesis testing. What are critical values? Critical values are the Z-scores that it's a borderline that separates significantly high or significantly low values from the rest. Now, do you remember what significantly high and significantly low represented? Anything greater than 2 standard deviations, both directions, right? That was using one of the methods. We're going to have another one in this one. For these, because when we start dealing with hypothesis testing, there are 2 types of tests we can look at: a 2-tail test or a 1-tail test. Again, that A is supposed to be the alpha. It's the Greek symbol alpha. It's the fish thing. And what alpha represents, if we have a 2-tail test, we're looking at both of these areas. The critical values are both of those. If it's a 1-tail test, it's only going to be here or on the other side. These are called 1-tail tests. This is a 2-tail. Obviously, they got the names from 2 tails as opposed to just 1 tail. So what does alpha represent? When we get something called confidence interval. Level of confidence. You can pick, as a scientist, as a researcher, you can pick whatever level you want. But typically, we look at 5% and 10% levels of confidence. Or 0.05 or 0.10. So what does that correspond to? that corresponds to the percentage of information that's at the tails. If it's a 5% confidence interval, that means there's 5% of the data back here at both ends. If we have a two-tail test, what do you think we have to do? Not double it. Cut it in half. Because both of these together have to equal 5%. You have twice as many targets to hit. So that's what we're talking about. Because you see now, we're still just adding up stuff. Chapter 7 and chapter 8 is the culmination of all the stuff being put together. All right, so now let's look. Example, find the z-value of 0.025, which is one side of the two-tailed test. Okay, well, this all you need is write this stuff. Just that, that's all you need.
It's a zero. I'm sorry, what was that? The point.
Well, yeah, because it's
Okay.
0 point, because it's half of 0.05. The answer is about to be 1.96. How do we figure that out? We use a chart. Since it's the same on both sides, where do we look? Do we look at here or do we look inside here? 0.025. We look inside here because that's the 0.025 is the area of the ends of the tails. So we look for the number inside here. So we're looking for the z-value of it. All right, so 0.025. 0.0250 is right here. It's at 1.96. So in our picture, it's negative 1.96 here and positive 1.96 there. Those are our z values. What if I gave you the other one, the 0.050? If it was a one-tail test only, where would you find that number? 0.050. 0.050 is between both of these. 0.0505, 0.0495. It's actually in the middle of that. So if it's in the middle, 0.050 is 1.645. How do we get that? Take the average, yeah. Take the 1.64, 1.65, add them together and divide by 2, because it's halfway in the middle. If it's half in the middle, it's great. But then if it's not, then we have to look at proportionality of how far into that is it. And that's a whole nother calculation. Typically, we go, if a number is between two numbers, go to the one it's closer to and give it to that value. That's a rule of thumb. But if you want to be exact, then you have to do percentage wise, how far is it over to one side to the other? Because 1.645 is perfectly in the middle, so it's 50%. That was just easy. So it gets more complex if it's a little bit different. What if I'm looking for 0.05, 0.0503? 0.053 is closer to which number? 05. So I could either give it to the 0.4 number, or I could try to figure out it's 0.04 something. And that's a whole nother calculation we want to get into. All right. Here's some notes. When finding a value of z sub alpha for any alpha, this is a z alpha. Let me make it alpha, so we don't get confused. When finding a value for z sub alpha for alpha, note that alpha is the area to the right of z sub alpha. So in our charts, we have to do the 1 minus wherever the alpha is. Because our chart is only to the left. So we have to, since the z sub alpha is looking for the right only, in our chart, since they're all to the left, we have to do the 1 minus the alpha. Note sub 2. Do not confuse the z-scores with the areas. The z-score represents how far you are from the mean proportionally. The area is the region under a curve. How much of the graph is under the curve between the mean and the z-score, or whatever the value is. So don't get the z-scores and areas confused. Lastly, what we just did, if you know z and you want to find the equivalent x value, here's the formula for it. Z times our alpha, which was the first thing we did last time, to denominator multiply by it, and then we add our mu, our mean. And z can be positive or negative, because it all depends on what side of the line it's on. So far, so good. Everybody done? Well, we talked about this earlier, significance. If X is greater than 0.5 of the top part or less than 0.5 of the lower part, then we have a significant value. That's what we're talking about significance. We talked about that, what, 2 chapters ago? In chapter 3 or chapter 4, the level of significance. So this is where it comes into play, because now we'll start, well, in the course, we would start going in deeper on finding how confident are you, because the significance and the confidence levels are related to each other. The value 0.05 is not absolutely rigid. In other words, it's give or take. That's the problem with statistics as a general. Nothing is too rigid when it comes to the calculations in statistics. It is what it is. We have also a built-in error factor, margin of error, which we don't have that in mathematics. So this subject is very wishy-washy. That's why you can make it say whatever you want it to say. Actually, no, I watched a commercial yesterday. I was gonna record it for y'all. It's mostly the insurance commercials to older people, where it says that, I mean, the comment they made was exactly backwards on what the true statement was, but they said it so quick and then moved on to the next slide that people don't catch it. I'll find what it is and I'll tell you which one to look out for. But yeah, you should be more conscientious when you start watching all these videos and listening to stuff in the commercials. What's true, what's false? How many times do you listen to a commercial on the radio and they're talking nice and slow, The last second, they give you all the disclaimers. They don't want you to know what's true, what's false. Basically, it said, everything we just told you is a lie. Good luck. What's that? Exactly what it is. If you don't read the fine print, and that's why this is down here, it's the fine print. Given any population with any distribution, whether it's normal, whether it's skewed, whether it's deviated, whatever type, the distribution of a sample mean mu, a sample bar, can be approximated by normal distribution when the sample is large enough. N is greater than 30. Because if N is less than 30, we have to use a whole new scheme of calculations. And that comes in chapter 7 and chapter 8. It's called the T-charts. There are some very special cases of very non-normal distributions for which the requirements of N is greater than 30 isn't quite enough. So number 30 should be higher in those cases. Again, it's the iffy part. But 30 is usually the cutoff, whether we have a Z score, a Z test, or a T test. And that's a whole nother test, because I wish I had it here, but the T-chart has on the very top, whether you have a one tail test, 2 tail test, and what kind of confidence intervals you have. Then we talk about the central limit theorem. The central limit theorem says this: for all samples of the same size n, where n is greater than 30, the sampling distribution of X bar can be approximated by normal distribution of the mean mu and standard deviation rho over square root of n. Ooh. Where have we seen that before? Well, let's just finish. I'll write that there. So the mean is mu, and the standard deviation is rho over square root of n. What's that? No. I'll put it up there next. Just the writing. Because up until now, our standard deviation's only been rho. But now our central limit theorem says as our samples are all the same size and they're more than 30 of them, then we use it, and they're normally distributed. Remember, normally distributed means in a bell curve. In a bell curve, what does it mean? How are the mean, median, and mode related in a bell curve? They're all the same. They're all in the top dead center. All right, so if our data is nicely set up that way, then we can do these things. So that's what it's saying with the symbols that we're using. The mean is the mu. These are parameters. Why are they parameters? Because they deal with the population. They're parameters because they deal with the population. They're statistical values if they deal with samples. Here are the key elements of a central limit theorem. Central limit theorem and the sampling distribution of X bar. Okay, now, again, why is it X bar? Because that's what we're doing with our samples. As long as we have more than 30, we're doing good. Given the population of any distribution has a mean mu and a standard deviation of rho, the simple random samples all have the same size of the selected population. So far, everything that's what we've been doing with all along. Practical rules for real applications involving the sample mean X bar. The mean of all values is population mean. And this is how, so remember mu is the population mean. So this is how we represent it. Mu sub X bar, because it's the mean of all values of your population. The standard deviation of all the sample means is this. It changes now. Because now the standard deviation of all of X bar, why is it over radical N? Anybody remember? Yes. Well, what is rho made up of? What is the formula for rho? Remember, it's the square root of the variance, which is, in the easiest sense, summation of X minus X bar over N. It's the square root of that. That's the variance. Then when we took the square root of it, it disappeared. So when we divide by N, it's got to be the square root of N because we took a square root of that. Because rho is the square root of the variance. And since we took a square root to get that, we'll take a square root of N. The z-score conversion of X bar. So in here we have it. The mean of your sample minus the mean of your population over the standard deviation of all your sample means. What if the population is not normally distributed and your N is less than 30 or equal to 30? Remember, up until now, all of our n's had to be very large, larger than n. The distribution of x bar cannot be approximated by this normal distribution. And as I said, remember I told you earlier, we can't use the z methods, we have to use the t methods, which comes later on in the next few chapters. So if it's not normally distributed and the sample is less than equal or less than or equal to 30, we can't use we can't use any of these formulas. So you see why I took away 7 and 8, because it gets more complex from here and we only have 2 or 3 days left. I didn't want to cram your brains and make you all fail because of me. I want you all to do it yourself. The following new notation is used for the mean and the deviation of our sample mean. And here are the notations. The mean value of all the means, we just talked about those. This standard error of the mean. Okay, again, mathematics doesn't have any errors, but in statistics, yes, we have a standard error for the mean. That's your rho sub x bar. Or standard error of the mean, SEM. So if all possible random samples of size n are selected from a population with the mean mu and standard deviation rho, the mean of all sample, let me put those Greek letters in there. So mu and standard deviation of rho. With a mean mu and standard deviation rho. The mean of all sample means is denoted by rho sub by this. Right, I mean, rho sub bar, x bar. The mean of all samples is represented by, nope, that's not rho, it's mu. So the mean of all sub x's are the mu sub x, and the standard deviation of all sample means is denoted by rho sub x bar. Let's look at this. Safe loading of elevators. The elevator in a car rental building at San Francisco International Airport has a placard stating that the maximum capacity is 4,000 pounds or 27 passengers. Yeah, so what they're remember, these placards are made many years ago. What they're saying here is if you look at it, 4,000 divided by 27, they're saying each person weighs 148 pounds. That's 2 of me. That one of those, 2 of those equal 1 of me. So that again, and then so this converts to a mean passenger weight of 148 pounds when the elevator is full. Well, okay, it said mean passenger weight, which means the average of everybody's weights. Back then, everybody was bone thin. So, but then again, if everybody else was not, let's say there were 248 pounds, you couldn't get 27 people inside there in the first place. So it all works out that way. We still assume the worst case scenario in which the elevator is filled with 27 adults. And we could look at the body, we see that the average of the body weights in this data set is 189 pounds and a standard deviation of 39 pounds. So that's true. So they're 40 pounds under what the data says we are. And yet they haven't changed those placards. Find the probability that one randomly selected adult male has a weight greater than 148 pounds. Then find the probability that a sample of 27 randomly selected adults has a mean weight greater than 148 pounds. So go ahead, let's try to do that. A, find the probability that one randomly selected adult has a weight greater than 148 pounds. You're not taking any notes? So should I have a final exam in class? One randomly selected adult. We're looking for there is a greater weight. So we have the mean and deviation. The mean is 148 and the deviation is 20, let's see. No, mean is 189, deviation is 39. So what do we have to do first? We have to find the z-value and then find this, once you find the z-value, find the weight that's greater than it. So will the z-value be positive or negative? Negative, because it's to the left of the mean. So we'll use a negative chart. Let me put the negative z chart up there. Where do we, what number do we put up there? What's the z value?
Negative 1.0.
1.05. Okay, how did you get 1.05? It's for all those who haven't worked it out yet.
So the equation
Mm-hmm.
is x mean over standard deviation. So it's going to be 148 minus 189 over 39.
Very good.
Then you should get negative.
Negative 1.50. 1.05. 1.0012345. So it tells us that our value should be 0.1469. Remember, these values are to the left. We want greater than. Remember, these values give us less than. We want greater than. Or 85.
It's 1469, right?
1469, yeah.
Oh, yeah.
8531. Very good. 8531 is correct. All right, now let's look at the second one. Find the probability that the sample of 27 randomly selected adults has a mean weight greater than 148. Remember, now we have to use the new formula. So it's the same mu, 189. The deviation is 39 over square root of our sample size. How do we know that we're dealing with the distribution of sample means? So because we are now dealing with the distribution of sample means, how do we know we're using sample means? Well, yeah, because we're looking at all 27 of them, and that we're looking at 27 of them, and that comes with the entire sample of all of them, which is 30. Yeah, 30 is a number. And for requirements for part B, we can use normal distribution if the original population is normally distributed or n is greater than 30. The sample size is not greater than 30, but the original population of weights of males is normally distributed. So either one of those two things plus condition apply, we can use it because it's normally distributed. So now we use our formula here to find the z-score. Our value we have is the 148 minus the mean over standard deviation, gives us negative 5.46. Because we're using the sample of all the means, that's what we have to look at.
I see where you put this.
Right.
Oh,
Yes. And it gets this way as we go deeper and deeper, deeper. But there's a problem. What's the problem? What does Z represent? The Z represents how far the data is from the mean. In which reference? In standard deviations. So when this one says -5, are there -5 standard deviations? No. So because it's so far away of our graph, because it's further away than that, we're not for sure that it's going to be zero. There's always that one chance it's going to happen. So somewhere here should tell us. Oh, here it is. Right, all the way down here in the fine print. Note, for values of z below negative 3.49, use 0.0001 for the area. Because we're not 100% sure that it won't happen. We're just sure we're not very sure it's going to happen. Right, exactly. So you have to be very, very, very careful when you read these things, because if you look for negative 0.5 on the chart, it stops at negative 3.0, negative 3.5 or below. So it was 3.49. What that means is we're at -5 standard deviations out, which is at the very, you notice how this graph never touches the x-axis? Because we're never ever 100% sure something's going to happen, and we're never sure it's not going to happen. It may happen. Right. That's exactly right. Introduction, this is how far we can get, because that's the next part. I'll send you the videos on the rest of that. This is where we're going to end the course today. Introduction to hypothesis testing. Because everything we've done so far, we're going to presume that our data is normally distributed, because it doesn't mean we're going to have one form or another, or our sample sizes are going to be more than 30. So if it's more than 30, we don't have to have a normally distributed curve. So again, if you're going to do a test, you'll have 50 to 100 to 200 samples. Identifying significant results with probabilities. This is the important one. The rare event rule for inferential statistics. What does inferential mean? This is how we started off the course. The first day of course, we talked about inferential. What do you infer? We talked about inferences. What does inferring mean? Yeah. With after based on observation, everything, I'm inferring, I'm assuming that this is going to happen. Right? Yes. If under a given assumption, there's the assumed part, the probability of a particular observed event is very small, and the observed event occurs significantly less than or significantly more greater than what we typically expect with the assumption, we conclude that the assumption is probably not correct. Put that into words in English. If, under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less than or greater than what we typically expect. So the particular observed event is very small, the probability of it, and the observed event, it occurs more or less than typically expected, we can conclude that the assumption is probably not correct. Again, this goes on with the fine print. It sounds legalese. Well, but think about it. If the probability of what we observed is very small, if the probability is very small, that means it's not going to happen. It may not happen again. And now we have a second condition. Remember, when we had probability, it's this times this. Now if we have something very small and we multiply it by something even more small, then it becomes super small. The smaller it gets to zero, closer it gets to zero, it's not going to happen. The observed events occur significantly less than or significantly greater than what we typically expect. Those are the extreme cases, the outliers. we conclude the assumption is probably not correct because we can't prove it. So in other words, that's what we're looking at. If it happens in the very outer skirts of the thing, it's not going to happen. That's what we call, remember the values at both ends? Those are the critical values. Anything beyond that, we're not sure. So that's what the whole thing about hypothesis means. Let's see if I have the data set. No, it's body temperature. We're going to do that. But this is what the course, this is where we would end up here. We do a little bit of examples, but then in the next chapter, chapter 7, we would start looking at testing these hypotheses. And in chapter 8 is what would make a hypothesis. Here's our data we collected. Think about it. When you make a hypothesis, how are you going to prove it? Well, you have to collect data, analyze the data, find the mean, median, mode, variance, deviation, and then from there, put it in your z-score. Is it going to happen? More than not. Look at our 0.5 or 0.2025, 0.025. Is it falling in there? If it does, it's not going to happen. Throw it away. If it happens inside there, our observations were correct. And that's what the whole thing's coming, hypothesis testing. This is, again, I'm so interested that they put this in chapter at the end of this chapter 6.4. And then we set chapter 7, which gives us more tools. And chapter 8, let's start doing it. Chapters 9 through 15 is when we start going through specific calculations about what we're looking for. We have called ANOVA, AMOVA tests. We have correlation regression. Said, is all the data in line? If it is, then we can predict future occurrences. If it's not, then it's a swag. And so again, so that goes on in the rest of the stuff. And that's typically what calculus stats 2 is about. But again, I'm only going to test you guys, the grades I'm going to take from you guys only from chapters 1 through 6. If you think about it, that's still a lot in 5 weeks. I wanted to go through 8, but time just didn't allow it. I could go on 2 more days, but you guys would hate me even more because you wouldn't have time to catch up doing the rest of your work. And if you thought that stuff was hard, the stuff coming up would be more difficult. It's more lengthy. So that's it for the class.